In this paper, we begin by defining the pre-training loss function as L, N, DTR, where N represents the number of parameters and DTR stands for pre-training tokens. We utilize the scaling laws from the Chinchilla paper to derive this parametric loss function and to fit values for the constants A, B, E, alpha, and beta. We then make an assumption that the demand for inference is independent of the model size and token count. This implies that models of the same quality but with different parameter counts will receive the same number of requests. Our objective is to minimize the sum of training and inference flops, with the constraint of pre-training loss. We use the standard approximation of flops for transformer models with n parameters, 6n per training token and 2n per inference token. Due to the complexity of determining the optimal parameters and pre-training tokens analytically, we resort to computational methods. We use the Newton root finding method to solve for n and DTR, which allows us to determine the optimal parameter token counts. We then modify our objective to estimate the real-world cost of inference by taking into account hardware utilization. We introduce parameters for training and inference cost per flop, center and CINF, and consider the training, inference input, and inference output MFUs, model flops utilization. Our new objective is to minimize the total cost of training and inference under the constraint of pre-training loss. We use the approximations for flops for transformer models and account for heterogeneous hardware utilization and costs. In our analysis, we compare our inference-adjusted models' flop counts, parameters, and pre-training tokens to Chinchilla-style models across different loss values and inference demands. We illustrate the trade-off between flops and cost, providing specific examples of cost reductions and optimizations achieved by our approach.